Let's talk about some issues with squaring and absolute valuing. Suppose we had the integral 0 to 2 pi sine of t squared. It looks like this. This is actually too complicated for us to really do in Calc 1, but there are times we want to do something squared. So what could we do just to say something reasonable about this? There's a graph of it. What would you say a lower bound is? Well, the smallest value the function ever takes on is 0, so a lower bound of 0 seems to work. We'll skip the upper bound, it's kind of obvious. A guess, and this is a height of 1 here, a guess might equal a height of a half times 2 pi, or a total value of pi. And it looks like the guess would be at least pretty close to right. What if we tried to simplify? So we'll write, is this equal to, question mark, the integral 0 to 2 pi sine of t dt squared? Can I take the squaring out of the integral and just do the integral first without the squaring and then square the answer I get? Well, what would we get? We're going to do some big old parentheses and just look at the integral that's on the inside. So we'd get sine for a full wavelength. And what does that area equal? 0. All this stuff cancels out. So then if we square that, we get 0 squared. But we're pretty sure from what we first drew that the actual answer is above 0, not 0. So the lesson is you can't move squaring outside of an interval or integral or back into it. So you can't move squaring inside or outside of an integral. Or any other nonlinear functions, square roots, e to a power. Does it even work on linear functions? So let's ask. So if you had the integral of like a times sine t plus some vertical shift, well, you can move the a out because that's a constant multiplier. You take the integral of sine t dt, but then you wouldn't just say plus v, you'd have to say plus the integral of v dt. Not just v. Because the integral of v is v times t, not just v. So as much as we'd like to do algebra by moving stuff inside and outside, the only thing you can move in and out of an integral an easy way is any constant vertical multiplier. Even a plus something else, you have to take the integral of that. Can we try to be sneaky some other way? Can we say the integral of sine t squared dt equals 1/3 sine t cubed? That seems like we're just using the power rule, but we should check it with the derivative. What's the derivative of 1/3 sine cubed? That would be 3 times 1/3, so we're taking that derivative. Let me try that again. That would be 1/3 times 3 sine t squared. So far looking pretty good. The 1/3s are going to cancel, I get the sine t squared. But then I have to remember the chain rule. And that's going to give me a cosine, and that's not going to match the overall integral. So if it's a derivative that would end up needing a chain rule, we can't do it here in chapter 5.4. Maybe we can do it in chapter 6.1. So integrals involving the chain rule We have to wait until chapter 6.1. Okay, so that's all kinds of issues with squaring and other nonlinear functions. Let's do another one that's slightly more hopeful. How about the integral 0 to 2 pi of absolute value of sine of t dt? Let's graph that. So we'd have one sine wave bump, and then it would continue down below, but we're taking the absolute value, so it looks like that. That junction is at pi, here's 2 pi. Can we say the total area is definitely bigger than 0? Yeah, I think that's right, and a lower bound of 0 would make sense. When would we ever care about such a function? This is called a fully rectified sine wave. If you have, so it's an electrical engineering thing. If you have a sine wave going along as alternating current and you pass it through a circuit involving the right kind of diode configuration, all the negative values get turned into positive values, and that's the first step in turning it into a direct current DC wave instead of DC voltage instead of AC. So this is kind of important stuff for electrical engineering. Can we say that this is equal to the absolute value of 0 to 2 pi sine t dt? No, because that's the absolute value of 0. All the signs end up, all the positive bump cancels out the negative bump, just like we saw with squaring, because we're pretty sure the answer should be something bigger than 0. What we have to do is break this into two pieces where we can take the individual antiderivatives without too much trouble. I mean, here we know that this bump is equal to that bump, so we can just do the first bump and then multiply by 2. But in general, if you have an absolute value, you have to break the integral into pieces where the absolute value is doing different things. So we have to break into pieces where the absolute value kicks in. So we'd say the first piece is just ordinary, right? Integral 0 to pi sine t dt plus that second part, it was like that, but it was kind of the opposite of that. This would be the integral from pi to 2 pi, and instead of sine, I know how to take the antiderivative of sine, that's fine, but this isn't sine, it's absolute sine, but I don't know how to take the antiderivative of absolute sine. But I could say that this is negative sine in this region. So negative sine t dt. And then I could move the negative out, take the antiderivative as usual. Some textbooks and authors really like having us do integrals with absolute values, and then we have to find out where the function would be crossing the axis. That's where the absolute value kicks in, and then break it into integrals like that.